Yeah, hello all. Welcome to the next session on electronic devices. This is the last session related to module 2, and in this particular session we'll be looking into two different applications of the PN junction. In the previous class we had looked into the working principle of solar cells and also we understood about photodiodes. So in today's class we'll understand about what is called as photodetectors, how we can use a PN junction to perform photo detection, and also we'll be looking into how this PN junction can be used to work as LEDs, that is light emitting diodes. So in the previous class I had told you about the solar cells. See, these solar cells can also be named as photovoltaic cells. Why? Because they are generating certain potential across the PN junction, which in turn will deliver certain power to the external circuit, and that phenomenon is called as photovoltaic phenomenon. Yeah, which I forgot to mention in the previous session. So please understand this. Whenever I say solar cells, it works on the principles of photovoltaic, and then it can also be referred as photovoltaic cells. Now in today's class, first let's look into the photodetectors. What is the definition? How do you construct a photodetector? Coming to the working principle, and also we'll be looking into the certain parameters which you have to understand when we say photodetectors. Once we are done with this, then we'll go for the last kind of device that we are interested in, which is called as a light emitting diodes. Now, what is photodetectors? As the name itself says, these are the semiconductor devices whose functionality is to detect light energy. Yeah, so that is what the photodetectors basically do. Again, here we'll have a PN junction, and that PN junction will perform this photo detection. So how can this basically happen? Now, what is the construction that we need to have? So, in order to make this happen, what we'll be having is, we'll be having a P side region and an N side region, and in between these two regions, we have an intrinsic material, or in between these two regions, we'll have a lightly doped intrinsic material. Now, either this intrinsic material can be of truly intrinsic, or we just need a material which offers higher resistivity. So, what is intrinsic materials? The ones which does not have free charge carriers. Does not have free charge carriers means the conductivity is poor. The conductivity is poor indicates that the resistivity is high. Therefore, either we can have a truly intrinsic material, or if it is not possible, we can have a material which offers higher resistivity. Therefore, what all I need to have, let me just represent it. So, we need to have a P region, then we need to have an N region, and in between we need to have an intrinsic region. Let me represent this intrinsic region to be as I. Now, in which mode this particular photodetectors work? Yeah, so we know the reverse characteristics that we have already discussed in the previous class. This is your I and this is V. So this is the reverse saturation current that flows because of thermal excitation that takes place, and this current, whatever is absorbed, I can refer it as dark current. What is this current that I absorb? It is referred as dark current, which indicates it is because of the thermal energy that is being provided, and there is no optical source that is involved when I absorb this current, and it is minimal. Now, as I tend to make the light rays to fall on, what will happen as the intensity of the light increases? What happens? The generation of the charge carriers, EHP pairs, increases, and as a result, the amount of reverse current that I can find in the device also increases in magnitude. Yeah, so if the generation rates, I refer it as G1, G2, G3, as I tend to increase the generation rate, that is by providing more amount of light energy falling on the PN device, then what will happen? The reverse current also increases. Now, whatever this phenomenon that takes place, that has to happen in which condition? In the reverse bias condition, wherein your current is also negative and the voltage is also negative. Therefore, I need to connect my PN junction device to be in the reversed biased condition. Done? So, what I will do here, I will just take up and then I will connect a resistor, followed by, let me connect the P type to the negative terminal of the battery and N type to the positive terminal of the battery. And this is how the construction goes. Now let me just represent here these regions where there is a junction being formed in the dotted lines. Done? This is R, let this be E. And then how does the current flow? It is from the positive terminal towards the negative, and let me represent this reverse current that is flowing as IR. Now, let me just change the orientation of the PIN. So, let this be P, let this be I, and let this be N. Done? And then where do I need to connect this P to? A resistor followed by a reverse bias. Let me provide the supply to be as E, this to be as R. Now, what is that we are trying to do? Here we are doing detection of light. That means there is certain amount of light that has to fall onto the device. Therefore, I will show that through these arrows, and let me represent it as h nu, where h indicates the Planck's constant, nu indicates the frequency, and this indicates the photon energy, which you are already aware of. Done? Now, this kind of construction is what we refer as pin photodiodes. What are these referred as? Pin photodiodes, where PIN stands for the P-type material that you have, an intrinsic region in between, and an N-type material. Now, be careful with the spacing or the width of this P, N and I regions that you need to follow. Now, as you can observe, the width of the P and N regions are thin, whereas this is little larger when compared to that of these two. Now, as you can see, why am I making this thin? Because whatever the light energy that is falling onto the surface have to reach until this point, right? So, therefore, I ensure that these two regions are thin in layer and that is little bit thick. Now, why this is made little wider? Let's try to understand when we go through the working principle. Yeah. So, this is regarding the construction. I hope all of you are clear with the definition of the photodetectors and the constructional details of the photodetectors. Done? Now, we have left out a point why this has to be little widened, that we will cover up when we consider the working principle. Now, let us try to look into the working principle of the photodetectors. So, in order for you to understand, let me consider the energy band diagram during the reverse bias. So, how will I represent the energy band diagram? Now, this is how I will be representing. Now, what is this region? This is your P region, this is your intrinsic region, and this is your N region. Done? Now, what do we have in between these two? This is your energy gap, that is semiconductor energy gap. This is your ECP, that is the bottom energy level of the P-type conduction band, and this is EVP. If I consider here, it is ECN and EVN. Now, you know the Fermi levels. Here the Fermi level is near to what? The valence energy level, and then here it is near to the conduction energy band. And this has to be above that of the N side. So, this is EFN because it is in the reverse bias, and this is what? EFP. And you know all of these factors, right? Now, let's look into few more details. Now what am I trying to do? For this, I am trying to incident the light energy. Now when this light energy gets incident, you need to understand three different regions of operations. That is, in this region what will happen, in this region what will happen, and in this region what takes place. Now we know this is nothing but your depletion region that we have, and there is a certain electric field intensity that we experience, which is from this direction, that is from the right hand side to that of the left hand side. So that's what have been represented here. Now let's look into the P side first. Now when I tend to incident a light energy, and what is that energy? It is h nu. When that happens, what will be created? An electron hole pair is created, and this is the hole that is being generated, and an electron, so hole is always present where? In the valence band, whereas the free electron is present in the conduction band. So within the valence band I am representing the hole. What about the electron? The electron, free electron, is in the conduction band of the P side. Done. Now this electron, what it will tend to do, either it will wander around in this particular conduction region, or by wandering around what will happen is it will tend to get diffused into this intrinsic region. Now once it gets diffused into the intrinsic region, this electric field, what will it do? It will drift this electron towards the inside. Understood with this? Yeah. So an electron hole pair is generated. Hole you have to represent in the valence band, electron you have to represent in the conduction band, which is a free electron. When this free electron tends to get diffused, what will happen? It will be drifted towards the inside. You know this, yeah? Now let me just erase this. You already know that diffusion happens and then followed by the drifting. So let me just represent this region as electron diffusion. So this is the region where electron is getting diffused, right? Afterwards the drifting happens, whereas the hole, it is already there in the valence band. So there is, and also the electric field will not let these holes to get diffused, hence it will be here only. So that's why I say this region to be electron diffusion. That is only for your understanding, understand. Yeah. Now when I consider, let me consider the N side. Now when I consider the N side, let me think that there is a light energy which is being incident. What is the energy of that light photon? It is h into nu. When that happens, we know an electron hole pair is generated. This is the hole that I am representing, and this is the electron that I am representing, which is a free electron, and this is the hole in the valence band towards the N side. Now this electron, yeah, it will be staying here only, right? What about this hole? This hole now tends to wander around, and once it reaches here, it gets diffused into this region. Once it diffuses, and then it gets drifted towards this region because of the electric field. Got this point? Yeah. Now therefore what can I say this particular region to be as? A region where the hole gets diffused. So I'll just say it as hole diffusion. Yeah, understood with these points. Now what about the region that is the depletion region or the transition region? In this region, whenever there is a light that is getting incident, what will happen? An hole and an electron, I'll just show it in an arrow, and a hole and an electron is being generated. Now where will this hole get moved to? Because of the electric field intensity, these holes get drifted towards the P side. Therefore let me show the arrow direction in this way, and these free electrons tends to get drifted towards the N side because of the electric field intensity. Hence I show the arrow direction in this way. Done. And whatever these carriers that is being generated because of the incidence of the light energy is what we refer as photo generated carriers, or simply we can say it as photo carriers. I hope all of you understood with this keyword, right? Now, because of this photo-generated carrier, what is this? This is a photo-generated electron. This is a photo-generated hole. Now, because of these photo-generated carriers, what is getting increased? The amount of electrons that is present in the conduction band of the N side and the amount of holes which is present in the valence band of the P side tend to increase. So, once the charge carriers increases, what happens to the reverse current that is flowing in the device? Even that will tend to increase. Getting my point? Clear till here? Yeah. So, that is how whenever I provide a light energy, the intensity is more, the light or whatever the current that is induced, the reverse current that you can see in the device also tends to increase. Now, whatever that current which is being generated are referred as photo current. So, what is that being referred as? Photo current. Now, if that photo current is purely or is primarily because of the photo carriers which is generated in the depletion region, if it is primarily because of the carriers which is generated within this depletion region, then such kind of a device is what we refer as depletion layer photodiode, because the charge carriers that is primarily because of the depletion layer, the reaction that takes place in the depletion layer. Hence, we say such kind of a photodiode or a photodetector as a depletion layer photodiode. Therefore, the three keywords that you have to understand in the working principle is what does photocurrent mean, what does photo generated carriers mean, and what does depletion layer photodiodes mean. Done? Now, we are not yet completed. We need to understand certain parameters which is related to the photodetectors. What that parameters relates to is, now as I know, this device is meant to perform the detection of the light energy. Now, is it not important for this device to detect the light when the intensity changes? That means, is it not important for this device to detect the light energies of different intensities? Yes, it is very much important, right? So, in order to understand how that basically happens, for that we need to understand few parameters, or what are the important parameters that we have to look into in order to ensure that my photodetectors are detecting the light energy within the certain intensity range. So, that is what we will be looking into under the parameters. Done? Now, let me consider the very first parameter, that is quantum efficiency. Let me just write it here. It is quantum efficiency, and the short form for this is nu of Q. Yeah, this is parameter number 1. Now, what does this quantum efficiency indicate is, out of the photons that is impinging on the pin photodiode, how many of them are successfully be able to generate the photo carriers, which in turn will helps in the increase in the current flow. Yeah, so that is what the quantum efficiency basically defines, or it will say. So therefore, if I want to mention the quantum efficiency, it is given by the ratio of the number of carriers which is generated per unit area per second to that of number of photons shining on the surface of photodetector per unit area per second. So, how many photons are reaching this surface and out of all the photons that is impinging on this surface per unit area per unit second, how many of them are successfully able to generate the EHP pairs? That is nothing but the photo generated carriers, and that's what will basically tell the efficiency, that is a quantum efficiency, which is a figure of merit for a photo detector. Now, how will I represent this number of carriers generated per unit area per unit second? So, per second. So, how does it be basically given as? It is given as JOP divided by Q. Now, what does that JOP basically indicates as? It is the optical current density divided by the charge. Done. So, that defines the numerator factor. Now, what happens to the second factor, that is the number of photons shining on the surface of the photodetector per unit area per unit second, is basically given by the optical power upon the surface to that of the h nu, that is the energy with which this photon is getting incident. Yeah, so this basically defines the efficiency, that is the quantum efficiency. I hope all of you understood with this first factor. Yeah. Now this quantum efficiency, what is the maximum value of this quantum efficiency if I consider for a pin diode? If I consider for a pin diode, this quantum efficiency can reach up to a value of 1. Yeah. Now, whatever the pin diode that I have, when I consider this pin diode, I need to understand whether this pin diode, can it absorb or can it detect the light energy which belongs to low intensity? No, it is very difficult for all the pin photodiodes to detect the light which is of low intensity. So, in order to make sure that it also detects the light with its low intensity, we will be coming across a second kind of photodiode or a special kind of photodiode which is called as avalanche photodiodes. Now, what is that avalanche photodiodes is? I'll just erase this. Now, in order to detect the light of lower intensity, we need to have a special kinds of photodiodes. What are these photodiodes are referred as? These are referred as avalanche photodiodes. Now, as the name itself indicates, what is the phenomenon? It is avalanche breakdown. That means I will be having a pin photodiode that will operate near to that of the avalanche breakdown region. Now, we know when the avalanche breakdown happens, what happens to the carriers that we have? It gets increased. The carrier multiplication takes place. As a result, enormous amount of current flows across the device. Therefore, if a single photon gets incident on the particular pin diode which works as an APD, then what will happen? The carriers which is generated, the EHP pair which is generated, will ensure whatever the amount of current that flows is multiplied by 100 times. Because of which enormous amount of current flows, and then what happens to the quantum efficiency? It will be more than 100%. That is for which kind of photodiodes? It is for the avalanche photodiodes. Now, what is the purpose of having these avalanche photodiodes? Is to detect the lights which is of low intensity. All of you are clear till here? So, that is regarding the first parameter, that is quantum efficiency. Now, let us look into the second parameter, which is response time. Now, in order to understand this response time, so within this, we will also be covering why the width of the intrinsic material is widened. Okay. Now, what is the meaning of response time? That means it is the amount of time that your photodetector takes to sense the change in the light intensity. So, whenever the incoming light changes its intensity, how much time your device takes to detect that change in the light intensity is what we refer as a response time. Yeah. Now, how can I define this, or what are the factors that I have to look into in order to ensure that this response time is as less as possible? Lesser the response time, more can be the more the device can detect different ranges of intensities of light, right? So I need to ensure that this response time is as less as possible. Now, how can I make that happen? So in order to make that happen, we need to understand, or we need to take up three different parameters. So what are the three different parameters that I have to consider is the diffusion time, then the second is transit time, and then the capacitance across the depletion region. Now, what is this diffusion time is? Let me just consider the same diagram. Now, in this particular diagram, as I mentioned, there is an electron that is getting diffused into the intrinsic material. Similarly, there is a hole which gets diffused into this, and then it is diffract to the P and N regions, right? Now, when this diffusion happens, now tell me, does that diffusion have to take place at the faster rate or at the slower rate in order to identify different intensities of light? See, that diffusion process have to take place in a shorter period of time. Yeah, that is what the diffusion time here I am referring to. So now to ensure that the diffusion time that it takes is less, how can I ensure that is by making this P and N regions to be as thin as possible. One of the reasons for making this thin was to ensure the light will reach till all the semiconductor layers, whereas the second reason that I make these two layers thin is because whatever the diffusion that takes place, that is the whole diffusion towards here and the electron diffusion, have to happen as fast as possible. Therefore, if I make that regions to be thin, it has to traverse, the distance that it has to traverse is less. As a result, the time that it takes to respond will be less. Done. Therefore, in order to have a less diffusion time, what is that I need to make? P and N width should be thin. Done. Now, what is the second parameter that we have in order to ensure the response time is less? The second parameter that we have is what we call as a transit time. Now, what does this transit time indicates is, it is once the photo carriers are being generated within the depletion region, they have to transverse through under the influence of electric field and get swept by the N type, and these holes have to transverse through and get swept by the P type. Now, whatever this time that it takes to transverse and reach the P region and this electron to transverse and reach the N region is what we refer as transit time. Now tell me, if I want more number of carriers to be transited or transversed in a faster rate, yeah, will that have an impact, or will that be impacted by the width that I have in the depletion region? Yes, therefore, the width plays an important role in the deciding the transit time. And one key point you need to understand is, whatever the carriers that we have generated have certain amount of lifetime, that is an average lifetime, which means before the recombination happens, it has certain amount of average lifetime. So this average lifetime have to be more than that of the time it takes to transit towards the P region and the N region. Done. If that does not happen, then the recombination will happen and it is of no use generating the EHPs. So always ensure the average lifetime of the holes and the electrons which is present here have to be more than that of the time it takes to reach the P and the N regions, that is the transit time. So that will be decided by the factor, that is the width of the transition region. Now along with that we have a third parameter. What is this third parameter? It is C depletion. What does the C depletion indicate? It is the capacitance that exists in the depletion region. Now how did we get this capacitance? See, when I consider the transition region, there are charge carriers at both the ends and in between we have an intrinsic material. Now does it almost look similar to that of the capacitance behavior, and that's how we get the behavior of capacitance in the depletion, and that is what we refer as C depletion. Now we know the basic equation for the capacitance. It is A into E A into epsilon divided by D, which indicates as the distance between the plates reduces, the capacitance increases and vice versa. Now keep this point in mind. Now tell me, does the width has something to do with the capacitance that exists? Yeah, it is there. Therefore, both of these have something to do with the width. Now, why do you have to worry about the capacitance is, we know the time delay is given by R into C. Now, this C is nothing but the capacitance. So, what does this indicate? The time delay. More the capacitance, more will be the delay time, less will be the response time. Therefore, I need to ensure the delay is small or delay is less, which in turn have to ensure the capacitance is less, which makes my response time to be as quick as possible. Therefore, these two factors has something to do with the width. Now, let me consider the width and let's see if in case it is small, what all factors it will impact. If in case it is large, what it will impact. Now, what are the factors that I have to consider? It is the transit time, then comes the C depletion, and then one more factor let me consider, it is the absorption rate. Now, when the width of the depletion region is small, what happens to the transit time? Smaller the distance, smaller it has to traverse, therefore the transit time it will be reduced, whereas if in case the width is large, more amount of time it takes to traverse, therefore the time that it requires is more. That's why I have written in the upper arrow direction. Now let me consider about the C depletion. Now what happens to the capacitance? As I reduce the width, what happens to the capacitance? It increases, which in turn will increase the delay. Therefore, the delay increases, the capacitance increases. Now here it reduces if I have a larger width. If in case I consider the absorption rate, more the space of intrinsic material, more light can fall upon and it can be absorbed. Less the space, less the absorption rate. Therefore, the smaller the space, less is the absorption rate, and wider the space, more is the absorption rate. Now, as you can see here, being the width on the larger side have more advantage when compared to that of on smaller side, because the C depletion is reducing, which in turn will help the time delay to be reduced, and the absorption rate is increasing, which is an advantage which helps you to generate more number of EHP pairs. Whereas the transit time is what will be increased, that you have to look into. Therefore, what you will try to do is, instead of keeping the width as small, you will ensure that it is of a size wherein it will not make a compensation, or it will try to make a balance between the transit time, the depletion capacitance that is absorbed, and the transition rate. Yeah, therefore I have kept it larger when compared to that of, wider when compared to that of the P and the N regions. I hope I have answered to all the doubts that you have. Therefore, we are done with the quantum efficiency and the response time. Now comes the spectral response range. Now what does this basically indicates is, it is indicating the range or the frequency range with which your detector can detect the light intensity. As I mentioned, your detector cannot detect the lights of all the intensities. There is a certain range that, therefore you need to ensure that if in case you are using a photo detector, within what range of spectrum it can be able to detect the light, and that is basically dependent on what is the EG value that you have. Based on the EG value, it will relate to the frequency of the light, which will in turn help you to detect or understand what is the range of light it can detect with the given photo detector. Then comes the detector responsivity. Now what does this detector responsivity indicates as? It is related to the gain factor, which indicates the ratio of the output current to that of the input light energy. Input light or input optical power. So what does this detector responsivity indicates? It is the ratio of the output current that you are observing to that of the input optical power. And these are the factors that defines the parameters of the photodetectors. Now I hope all of you are clear with the photodetectors that we have considered. Now let's look into the second kind of, or the last device that we have in second module, which is light emitting diodes. What is this light emitting diode? As the name itself indicates, it is a kind of a diode which emits light. That means this is a device wherein you are providing certain electrical energy or an electrical supply, and then that through that what it will tend to do, it will try to perform the light emitting. So from the electrical energy to the light emission, that is what the functionality of the LED is. Now in order to perform that, let's try to understand how does it basically work. So the constructional details are simple, you need not to worry about that much. So if in case I consider here, this is made of P type, this is made of N type, and then what do we have in between? It is the depletion region, and that's what I am trying to represent here. Done. Now one key point you have to understand is the light emitting diodes are basically working in the forward biased condition. See, when we consider the photodetectors, it works in the third quadrant, which is reverse biased. When I considered this solar cells, it was working in the fourth quadrant. Understand this again, that we did not have any external bias because that is the device which provides the power to the external circuit, whereas here in case of light emitting diodes, we make them to operate in the forward biased condition. Hence, how do I need to connect this PN junction to a positive terminal to the P side and a negative terminal to the N side, and let me represent this as R and this as E. Now how does the current flow? This is how the current is flowing. Done. All of these factors you know. Now let me just represent . This is how the electric field direction is. What do we have? Immobile negative and positive ions, yeah, and then here majority carriers are holes, here the minority carriers are electrons. Done. I hope you can make out the difference. Done. Now this is a structure that we have. Now how does this basically light emitting diode works? That's what we are trying to understand here. Now when I tend to provide a forward bias, what will happen to the depletion region? It tries to shrink. Now when that shrinking happens, what happens to the diffusion process that takes place? It can happen at the faster rate. Now what is that basically diffusion indicates? It is the electrons which is present here is trying to occupy the holes that is present in the P side, and the minority carriers electrons present here is trying to occupy the holes that is present here. Getting my point? Now when this basically happens, we have understood two different kinds of semiconductors. What are those? Direct band gap semiconductors and indirect band gap semiconductors. So in case of indirect band gap semiconductors, see, this is the conduction band and this is the valence band. What do we have here? We have electrons here. Right. Now, when I provide certain potential, what will happen? An electron will get enough energy and then it will move on to the conduction band. Right. Now, what is this referred as? And there is a hole that is being generated and this is referred as Ehb generation, which you already know. Now, once it is generated, can this stay in a longer period of time here? No, it cannot. Therefore, what will it try to do? It will try to recombine with the hole that is present in the valence band. Now, when this recombination happens, we had classified two different kinds of semiconductors. That is indirect band gap and direct band gap semiconductors. In indirect band gap semiconductors, when this recombination happens, then it will provide certain output energy. That energy is that energy will be in terms of heat energy. Done. Whereas, when I consider a direct band gap semiconductor, when this recombination happens, this will certainly output some energy and that will be in the form of light, which we have already discussed. In indirect, it will be in the form of heat, whereas in the direct band gap, it will be in the form of photon energy. Now, tell me, when this electron have to move here, then it has to have an energy which is slightly more than Eg. Yeah, therefore, for the generation of the free charge carrier, it needs to possess a semiconductor energy which is greater than that of the semiconductor band gap. Now, when this recombination happens, so whatever the output energy that it will give, that energy will be slightly less than this Eg. Keep these points in mind. Done. Now, why am I saying these factors is, now when this recombination is happening in the case of direct band gap semiconductors, what is that being output as? It is the light that is being outputted. Done. Now, when this light energy is being emitted out, yeah, I need to absorb this light energy so that I can show different colors. That's why what will I try to do is, I will try to place some encapsulation or a dome like structure. This is where I am obtaining the photon energy which is outputted because of the recombination. And then I will place a dome like structure. This dome like structure will ensure that whatever the refractive index difference that I have between the semiconductor bar and the air is in such a way that it will not go beyond the critical angle that will make the total internal reflection. So, I need to avoid the total internal reflection. Therefore, what will I create? I will create a dome like structure. This dome like structure will ensure that there is no total internal reflection that takes place, and all the light energy that I am getting out of this semiconductor will tend to go towards the outside medium. Done. And this is what we refer as a light emitting diode. Now, one key point here you have to understand, which is very much important. Now, what kind of material I can use, what kind of semiconductor materials I can use which can act as a light emitting diode. So, if I use a particular semiconductor material, it has to have a semiconductor band gap which should be equal to 1.24 divided by lambda micrometer, and this is electron volt. So, only when my Eg satisfies this condition or it is more than this, then only such kind of semiconductor materials I can use for LEDs. Now, why is that so? Because all the light intensities cannot be detected by the human eye. We have a certain range, right, like IR range, UV range and the visible range. Only the lights which is present in the visible range have certain frequencies which can be detected by the human eye. Therefore, I can use the LEDs which can detect the light within the visible range. So, for that we need to have certain compound semiconductors which has Eg value somewhere near to this. Yeah, so that is why this plays an important role when I consider a light emitting diode. Now, can I use silicon and germanium for this? No, Eg value is not greater than that of this, because of which I cannot use it as a light emitting diode, and also we know that it belongs to an indirect band gap semiconductor. Similarly, germanium also belongs to indirect band gap. Both of these will, when recombines, will generate heat, not as light energy, therefore we cannot use silicon and germanium. Whereas what are the other alternatives that we can have is the compound semiconductors. Now what are the different compound semiconductors we can have? One is gallium arsenide or an indium phosphide. Now these two will generate the light which is in the range of IR, yeah, which is not in the visible range. Now if I want to have the lights which is in the visible range, and if I want red or yellow, then what I'll do, I'll put up certain composition of gallium arsenide and then phosphide in a certain composition so that I can get these colors. Similarly, if I tend to reduce the arsenide content and then increase the phosphide content within this, then I'll be getting different colors like red to green. Yeah, so these are the different compound semiconductors that I can use to obtain different colors. Now where are these different colors we have used in the practical cases? When I consider the IR, the remote controls that you are using, where you cannot see the signal that is being sent to the TV, right? So that is where the gallium arsenide and indium phosphide comes into picture. Whereas the gallium arsenic phosphide and then gallium phosphide, it produces red, yellow and green, and these signals are the ones which is being used in the traffic lights. So that is where the example that you can find. And also the TV screens that you have which has different color compositions, or the display boards, smart display boards that you have. So those are all the places where these LEDs find its applications. One thing you need to understand here is, if in case there is any defect in the semiconductor, then when the recombination happens, it need not provide a light output energy. So you always have to ensure that the kind of semiconductor materials that you are using is free of defects. So only if it is free of defects, when the recombination happens, you can get the light output energy. If not, it is not possible. And then if I want to measure the efficiency, external efficiency of this LED, it is given as the product of internal radiation efficiency into extraction efficiency, which indicates out of how much current that I am giving to the PN junction, how much light energy that I am extracting out. So that have to be, that relationship is what basically this external efficiency indicates, wherein this internal radiation efficiency is nothing but how much recombination can generate how much light energy, and then extraction efficiency indicates whatever the light energy that is generated, how much percentage of that can be given to the external surrounding, and that's what this external efficiency indicates. Yeah, I hope you are clear with this particular equation. And in order to ensure this is maximum, you need to ensure that for internal radiative efficiency to be maximum, you need to ensure there is no defects in the device. In order to ensure the extraction efficiency is maximum, you need to have a dome-like structure instead of a planar structure. Now, if in case you have a plane-like structure, what will happen? The semiconductor refractive index is more than that of the air. As a result, the angle with which the light energy incidence on the planar surface will be more than critical angle, which in turn results in total internal reflection. And I don't want this total internal reflection to happen. So avoid that. What I'll do, I'll try to have a dome-like structure. I'll try to have an encapsulation. You can also say it as an encapsulation. So this is all about the working principle, the factors that you have to consider while taking up or choosing a particular material which to act as an LED, and the different kinds of applications and the different kinds of materials which provides different colors. Yeah, I hope all of you have understood related to the LEDs and the photodetectors. Now, one more thing is inject electroluminescence. Now, what does this inject electroluminescence basically indicates is, it is nothing but the phenomenon or the effect that occurs wherein when the recombination happens, there is a light that is being outputted, right? So that phenomenon or that effect is what we refer as inject electroluminescence. Yeah, so these are the keywords that you need to be aware of under each of these topics. I hope all of you are clear with the topics that I have covered in second module. Yeah, this completes module 2. From the next session, we will start off with module 3. Thank you one and all. Have a good day.